In this video, we are going to take a look at oxidation states or oxidation numbers. We're going to take a look at what they are and how to determine them and why they're even useful to learn in chemistry. So let's start out with the definition of an oxidation state. Now, sometimes you see them called oxidation numbers. Both of those words are interchangeable. So an oxidation state represents the charge that an atom would have in a compound if the compound were composed of ions. So what does this actually mean? Well, you could take something like, for example, water. Let's look at a molecule of water. Now, we know that this is a covalent compound. However, if it were ionic, then we would say that the oxygen would gain 2 electrons, so it would have a -2 oxidation state, and each hydrogen would lose 1 electron, so they would have a +1 oxidation state. So it's kind of weird to think about, but it really is just talking and describing the number of electrons that are either shared or transferred when forming a bond. You can think of it that way. Now, why are they useful? Well, you'll see in other videos that it can be really useful to follow chemical reactions by looking at changes in the oxidation states of the atoms in each compound during the reaction. We're actually going to use that in other videos to take a look at definitions of redox reactions, for example. They can also play an important role in some of the nomenclature of chemical compounds, and we'll take a look at some of that nomenclature later on in this video. So before we get into some examples of how to assign oxidation states, there are several rules that we do want to go over. So the first rule here, the oxidation state of any free element is 0. So what that means is if we had, for example, oxygen, even though it's O2, its oxidation state would be 0. And that's because if we took a look at this molecule of oxygen, we have the 2 oxygens bonded together, but they have equal electronegativity. And so the electrons are being shared equally, so equal sharing across the bond between those elemental compounds, which means we're not having really any transfer of the electrons back and forth. And so that means that the oxidation state is going to be 0. So things like nitrogen, that would be 0, or you could have chlorine, that would be 0, or you could have just like single elements like magnesium, that would be 0 as well. So any free element is always 0. The second rule, the sum of the oxidation states of all atoms in a neutral compound is going to be 0 as well. So for example, if you had MgCl2, then the oxidation state for chlorine, it's always going to gain an electron, so that's going to be -1. We have 2 of those, so that means the magnesium is going to be +2, because +2 plus 2 times -1 is going to give us 0. Our third rule says the sum of the oxidation states of all atoms in a polyatomic ion is equal to the charge of the ion. So if we had, for example, a nitrate ion, then all of the sum of the oxidation states here would equal to the charge, which is -1. Now, oxygen, it's always going to gain 2 electrons, so it's going to be -2. And since we have 3 of them, and we're going to know this is going to equal to -1, and nitrogen, we don't know what that is. If we take a look at it, we have 6 minus 1, so that would give us a +5 oxidation state. Okay, so +5 plus 3 times -2 is going to equal to -1. And finally, on this slide, the oxidation state of fluorine is -1 in all compounds. So just an important one to know. A few more rules. So the oxidation state of group 1 metals is always +1, and group 2 metals is always +2. The oxidation state of oxygen is always -2. There's a couple of exceptions though. In the compound OF2, where fluorine is more electronegative, the oxidation state of oxygen is actually going to be +2, and the fluorine will be -1. And then in peroxides, oxygen is going to be a -1 instead of a -2. So just a couple things to kind of keep in mind. And finally, the oxidation state of hydrogen is +1 when it's combined with more electronegative elements, so most nonmetals. And it'll be -1 when it's combined with less electronegative elements or metals. Hydrogen in a -1 oxidation state is called a hydride ion. So hydrogen can be +1 or -1 depending on if it's combined with a metal or a nonmetal. So let's take a look at a couple of examples. We're starting off with CaO. CaO, let's use the rule that oxygen always has a oxidation state of -2. And we're also going to use the rule that because this is a neutral compound, they need to add up to 0. So if we say calcium is X and we solve for this, X is +2. And so that means that the oxidation state for calcium is +2 and oxidation it's -2. Now, really important to note here, we always put the positive or the negative signs in front, never behind for oxidation states. Okay, our next example here, actually let's maybe do MnNO4 -2 to start with. So if we say manganese is X, because we're not quite sure what that is, we've got that, but we know oxygen's going to be -2, and we've got 4 of them, and we know that needs to equal to -2. So we have X minus 8 is equal to -2, or X is equal to +6. So that means that the oxidation state of manganese here is +6, and for oxygen, it's -2. Looking at NaNO3, sometimes with ionic compounds, it's better to think of the ions separately because then it's pretty easy. If we have an Na+, that means that that is a +1. And then the NO3-, the oxidation states would have to add up to -1 here. So not sure what nitrogen is, but the oxygens, we have 3 of them and they're always -2. We know that needs to add up to -1. And if we did that math, that would give us +5. So sodium here would be a +1. Nitrogen would be a +5. And then oxygen would be a -2. So that's how we go through and we assign oxidation states or numbers. Now, we can use these as naming conventions for our oxyanions. So this is really interesting. We could take, for example, our generic name of sulfate, and instead of in sulfite, so we'll look at these 2 examples here. If we went through and assigned oxidation numbers, this one is +6 for sulfur, and this one's +4. So instead of using the sulfate-sulfite naming convention, we could instead call this sulfate and then use the Roman numeral 6. And we could call this one sulfate with the Roman numeral 4. So we could use these Roman numerals at the end of the polyatomic name in order to indicate the oxidation state of the element that's not oxygen in these polyatomic ions or these oxyanions. So we could do the same for nitrate versus nitrite. And if we do oxidation numbers here, nitrogen's +5, and then this one, nitrogen's +3. So we could instead call these nitrate 5 and nitrate 3. So it's a little bit easier. You don't have to memorize the 8s and the ites. Instead, you can use the oxidation numbers to indicate. For the last one, we have chlorate versus chlorite. And the oxidation numbers here, if we work them out, we got +5, and we got +3 again. So instead we could call these chlorate 5 or chlorate 3. All right, so both naming systems are fair game. They're both used. Just kind of knowing that there are two possible naming conventions for these oxyanions. So that is how you figure out oxidation states and how you use them in nomenclature. That's it for this video. We'll see you in the next one.